In this video sequence, we'll learn about acid-base reactions and how to identify the acid, the base, the conjugate acid, and the conjugate base. We'll learn how to draw the products of an acid-base reaction and how to indicate the flow of electrons and equilibrium with the appropriate arrow formalism. In this first video, we'll introduce and define acids and bases, and we'll discuss the equilibria of acid-base reactions. We'll start with the Bronsted-Lowry definition of acids and bases. And here an acid is a proton donor, while a base is a proton acceptor. In order to accept a proton, a Bronsted base will typically need a lone pair of electrons that will be used to form the new bond with the proton. In this example, HCl is reacting with water. HCl, hydrochloric acid, is the acid. It's the proton donor. And water is the base. It's accepting the proton from HCl. The products of the reaction are the chloride anion and H3O+, the hydronium cation. And these products are also acids and bases. The chloride anion can accept a proton and so is also a base, and so we call it the conjugate base of the reaction. And the hydronium ion can donate a proton and so is an acid, and we call it the conjugate acid of the reaction. It's the new acid formed from the acid-base reaction given. When we draw these reactions, or any reactions really, we can map the flow of electrons during the course of the reaction using curved arrows. Similar to the arrows we used when discussing resonance structures, our curved arrows will begin at the source of the electrons and end at the destination of the electrons. So in this particular reaction, where the lone pair on the oxygen forms a new bond with the proton from HCl, I draw a curved arrow that originates at the oxygen lone pair and ends at the proton of HCl. This first arrow indicates the bond formation between the oxygen and the hydrogen. Then we have a second arrow that begins from the electrons in the HCl bond and ends at the chlorine atom. This second arrow indicates that the HCl bond is broken, and the electrons in that bond move to the chlorine, resulting in the chloride anion. And so more generally, we can depict an acid-base reaction in the general form shown here at the bottom. The reaction of HA, the acid, with B, the base. And notice that we draw a lone pair on B, the base. And this general acid-base reaction forms A-, the conjugate base, and HB+, the conjugate acid. Notice also that the acid, upon losing its proton, becomes the conjugate base, and the base, upon gaining the proton, becomes the conjugate acid. Let's pause for a concept check. Here, use the appropriate curved arrows to map the flow of electrons in the acid-base reaction shown. Then let's also identify the acid, the base, the conjugate acid, and the conjugate base. In this example, we have HCl again, and so HCl, or hydrochloric acid, will be our acid. The amine with its lone pair will be the base. That means that the lone pair on the nitrogen will attack or bond with the hydrogen from the HCl. So I draw a curved arrow from the nitrogen lone pair to the hydrogen. Then the electrons in the HCl bond will move to the chlorine as the bond is broken. So we draw a second curved arrow to show that electron movement. In this reaction, the HCl is the proton donor, so it's the acid, and the amine is the proton acceptor, making the amine the base. And looking at the products of this acid-base reaction, the chloride anion can accept a proton and is our conjugate base, and the ammonium cation can donate a proton and is our conjugate acid. Now that we've seen the basic anatomy of an acid-base reaction, we'll look at a couple of acid-base reactions involving water. And that's because water can act both as an acid or a base, a proton donor or a proton acceptor, and it depends on the reactant, if the other reactant is an acid or a base. In the top example, water reacts with acetic acid. Acetic acid is a good acid or proton donor, and so water will act as a base here. In this reaction, water will attack or accept the proton from acetic acid, and then the electrons in the OH bond of acetic acid will move to the electronegative oxygen atom to form an anion on oxygen. That will give us an acetate anion and a hydronium cation as our reaction products. The acetate anion is our conjugate base for this reaction, and the hydronium ion is the conjugate acid for this reaction. So notice again here that the acid, upon losing its proton, becomes the conjugate base, and the base, upon gaining the proton, becomes the conjugate acid. In the second example, water is reacting with ammonia. And ammonia is a good base, a good proton acceptor. And so in this case, water will act as an acid. The lone pair on the ammonia nitrogen will attack or accept the proton from water. And so we draw a curved arrow from the nitrogen lone pair to the water proton. And then the electrons in the OH bond move to the electronegative oxygen atom. This gives us ammonium and hydroxide as our reaction products. The ammonium is the conjugate acid, and the hydroxide is the conjugate base. Looking at these two examples of water acting both as an acid and a base, in order to predict which way it acts, we need to know if the other reactant is a good acid or a good base. And so in order to compare acidities and basicities, we need to learn a little bit about how we measure the acidity of an acid, how we quantify acidity or acid strength. We measure acidity and predict the reactivity of an acid using pKa values. The pKa of an acid is the measurement of the acid's tendency to lose its proton. Okay, the pKa is measured. It's an experimental quality. And it's measured for the reaction of the acid, HA, with water. This reaction has an equilibrium constant that describes the extent of dissociation of the acid. How much acid has protonated water at equilibrium? That equilibrium constant gives rise to the pKa value, which is just the negative log of the Ka, the equilibrium constant. So the pKa is a direct measure of how readily an acid will donate its proton. Okay. Because the pKa is the negative log of the equilibrium constant, a larger pKa describes a weaker acid. A smaller pKa describes a stronger acid. So always remember where these values come from. If the equilibrium lies to the left, that means the acid doesn't readily dissociate. The Ka value will be small, and the pKa, the negative log of the Ka, will be large. So a large pKa corresponds to a weak acid. If the equilibrium lies to the right, that means the acid very readily dissociates. The Ka is large, and so the pKa, the negative log of the Ka, is small. So a small pKa corresponds to a strong acid. Okay, so based on that, which acid here, water or HCl, is more acidic? Well, we just said that the smaller pKa correlates with the more acidic acid. So comparing our two pKa's, -7 is smaller than 15.7, so HCl is the stronger acid of the two. Okay, now we've seen how to compare acidities using pKa values. So when we have a reaction and we're not sure which component is the acid and which is the base, we can now compare the pKa values of the two reactants to determine that. So in this reaction of acetic acid and water, we've already seen, we said acetic acid is the acid and water is the base. But what if we didn't already know that? Then we can find the pKa values for our two reactants. These are in the appendix of your textbook, and we can compare them. And you can pause your video now and find them, make sure they match mine so you know where to look in the future. What you should find is that the pKa of acetic acid is 4.7, and the pKa of water is 15.7. The lower pKa indicates the more acidic species, and so acetic acid is the acid in the reaction. We'll draw in our arrows, and we'll also just note the pKa for the hydronium ion, which is very acidic and has a pKa of -1.7. Okay, now thinking about the overall reaction equilibrium, both sides have an acid and both sides have a base. So which direction does the equilibrium favor? Which side of the reaction will the equilibrium lie on? Another way to ask this same question is to ask which acid, the acid or the conjugate acid, is stronger. And here our hydronium ion, the conjugate acid, is stronger. That means that the hydronium ion wants to donate its proton way more than the acetic acid does. and so the reaction will lie to the left. And we indicate that the equilibrium lies to the left by adjusting our equilibrium arrows so that the one pointing left is longer and the one pointing right is shorter, as I've shown in blue. Okay, so a couple of takeaways here. In general, an acid-base reaction will always favor the weaker acid-base pair. So in our example, acetic acid is the weaker acid, and so the equilibrium lies toward the weaker acid, or toward the left. And second, the size of the forward and reverse arrows indicates the directionality of that equilibrium. Let's end this video with one more concept check question. For the example shown, which side will the equilibrium favor? Go ahead and decide, and then draw in the appropriate arrows. Okay, in order to answer this question, we need to identify our acid and our conjugate acid, and then compare their pKa values. Figure out which acid is stronger and which is weaker, and then the equilibrium will lie towards the weaker acid. Here our acid is acetic acid, once again, with a pKa of 4.7. And our conjugate acid is water, with a pKa of 15 or so. Water is the weaker acid, and so the equilibrium will lie towards water, or towards the right. So we indicate this with an equilibrium arrow, with the arrow toward the right being longer, and the arrow toward the left being shorter.